We'll look at how we can apply differential calculus to analyze the motion of an object moving in one dimension, aka along a line. So the first thing we need to start if we want to analyze the motion of an object is the position and displacement of said object. So an object's position at some time t is not really too interesting to us as physicists since the position does not tell us about which direction the object is heading. For example, a person is standing on a number line that's, let's say, x equals 6, where x represents our position, could be heading to the left of x equals 6, to the right, or standing still. So position does not tell us anything about what we want to know about our person. What we specifically need is their change in position to determine which direction they're heading. For example, a person heading from 0 to 4 would have a change of position of 4 units, telling us they're heading to the right. While a person heading from 4 to 1 would have a change in position of -3 units, the negative telling us that they're heading to the left. So change in position over an object, of the object over a certain time, delta t, is called the displacement. So instead of saying change in position, we can now say displacement. And then as an example, I highlight what we just talked about. So as physicists, in order to determine direction an object is heading, we're more interested in the displacement of the object than the actual position of the object. Again, the position will not be able to tell us which direction our object is heading. So now we move on to average and instantaneous velocity and speed. And what is the difference between velocity and speed? So the rate at which displacement x occurs over a certain time interval t is what we call the average velocity, the average of the object. Again, our average velocity is equal to our change in position, what we now call displacement, divided by change in time. If we want to find the instantaneous velocity is defined as the rate of change of position at a single time t, or the derivative of the position function. The idea being is that we take the limit as delta t goes to 0, which makes this a derivative right here, and thus it's a first derivative of our position function. Velocity is the first derivative of our position function. Lastly, we need to look at the speed of an object. The speed is slightly different from velocity. If you've had me for physics, you already know this difference. If you haven't, in physics we define speed and velocity as different quantities, despite the fact that we associate them as the same thing in everyday life. The idea in physics is that whereas velocity has a direction because it depends on displacement again giving us the direction that we travel, the speed of an object does not depend on direction. It's defined as the rate of change of position independent of direction. So as a result, speed does not depend on direction and will always be a positive quantity, never negative. So thus, in order to obtain speed, we need to mathematically make sure that our velocity is always positive. So the equation for speed is obtained by just taking the absolute value of our velocity function. And that's all we have to do for speed. Now we move on to average and instantaneous acceleration. Acceleration is defined as the rate at which velocity changes over a certain time interval delta t. So our average acceleration is going to be our change in velocity divided by our change in time. Similar to the last slide, we can define our instantaneous acceleration as the rate of change of velocity at a single time t, the first derivative of the velocity function, or the second derivative of the position function. The idea being is, again, we take the limit as delta t goes to 0 of our change in velocity or change in time, which gives us a derivative of a velocity function. And since the velocity function is itself the derivative position function, that means acceleration is the second derivative of the position function. So acceleration is the first derivative of velocity, second derivative of position. We can also associate acceleration with concavity due to the fact that acceleration is a second derivative. So the sign of the acceleration at a point t equals c is indicative of the concavity of the position function at the point. And this is going to be useful for when we come up with conditions for speeding down and slowing up. So if we have a positive acceleration, that implies our second derivative is greater than 0, so x would be concave up at time t equals c. Whereas if we have negative acceleration, that implies our second derivative is less than 0, so x will be concave down at t equals c. And that should say concave down. That's another typo on my part right there, just from copying and pasting. So these are the conditions that we should be familiar with for concavity and acceleration. So now we'll look at how we can apply the previous information to determine the direction an object is heading for some function, some position function x of t. So to recognize if our velocity is less than 0, since our velocity depends on displacement, that implies our object's heading to the left. Whereas if we're heading to the right, that means our velocity must be greater than 0 at our time of interest. So as an example, with this car right here, our person is heading towards the right here, so their velocity must be greater than 0. Now when our car is heading towards the left, they're heading in the leftward direction, so our velocity must be negative. If we're changing direction, that means we're going to be going from the right to the left or left to the right, all right? Which means we're going to be either going from positive to negative or negative to positive for our velocity. So our velocity is going to change signs, and as a result of changing signs, that means that our velocity briefly has to be 0 when we change direction. So for example, when this car right here makes a U-turn, our velocity will go from positive over this interval to negative right here, and then at this brief moment when we change direction, the velocity is going to be equal to 0. You can actually see this because it looks like a local extrema right here. So a nice little interesting aspect there. And we'll see how that applies to position graphs and velocity graphs in class. So again, to the left, velocity is greater than 0 or less than 0. To the right, velocity is greater than 0. And then if we change direction, our velocity will be equal to 0 and change signs at the specific time of interest. So as a result, we can apply the first derivative test to determine direction. The first thing we have to do is we have to find the first derivative of our position function, or the velocity function, since velocity is the first derivative of position. The next thing we're going to do is we're going to set v of t equals 0, and we're going to solve for t. And then in between each critical point, we'll evaluate v of t to determine the sign of velocity over the interval. And then we'll interpret the results just as we did with the first derivative test. If our first derivative, in this case a velocity function, is greater than 0 in between critical points, then that tells us our object is heading to the right over the specific interval of interest. So direction of an object is really nothing new to us. It's a first derivative test. It's just applied in the context now of physics. Very, very interesting. So cool. I love how physics is tied to math. So let's look at a brief example here. Determine the direction of motion of a particle whose position is modeled by x of t equals 1/4 t to the 4th minus 1/3 t to the cubed plus 8 for t greater than or equal to 0. All right, so again, we apply first derivative test, so we have to find our first derivative position, our velocity function. And in this case, the derivative of 1/4 t to the 4th is going to be t cubed. The derivative of minus 1/3 t cubed is going to be minus t squared. And derivative of h is going to be 0. So we get t cubed minus t squared as our first derivative, our velocity function. So we set this equal to 0 now. We can factor out a t squared. So we get t squared times t minus 1 equals 0, leading us to get factors of t equals 0 and t equals 1. So now we set up a velocity, now we set up the sign chart that we used with the first derivative test. We have v of t right here and then t on our number line. So we have 0 and 1. And then we test out points in between. So I can choose 1/2 for my first point. And when we do that, we see we're going to get a value of negative 1/8 for our velocity, which is less than 0. So that tells us between 0 and 1, our object is heading to the left. Now for our second test point, greater than t equals 1, we can use 2. And we're going to get that the value of our derivative of position, the value of our velocity, is 4, which is greater than 0. So that tells us for t greater than 1, our object is going to be heading to the right. Notice here that we don't test out any points for t less than 0 because the prompt states that t must be greater than or equal to 0. The idea being is that we always take time to start at 0 because whenever you time something, the timer on your watch always starts from t equals 0. Otherwise, if you have negative time, that implies you're a time traveler, like Marty McFly. That'd be pretty cool though. Not going to happen. Alas, not going to happen. So, what we can say is that time t equals 0, our object starts from rest. Since our velocity is equal to 0 at that time, that's what we did in the second step when we found the critical points. For t between 0 and 1, the object is heading to the left as our velocity is less than 0. And then at t equals 1, the object changes direction as our velocity, have to wait for this thing to drop down. As our velocity is equal to 0 at t equals 1, that is the second critical point, and v of t changes signs from negative to positive. Specifically, our object changes from going to the left to going to the right. For t greater than 1, the object moves to right as our velocity for t greater than 1 is positive. And that is all we need to do is just apply the first derivative test to our position function. So now we look at the location of an object. So another point of interest we may be interested in with analysis of an object's motion is determining when an object is farthest from its origin. Okay, so when this happens, that corresponds to an absolute maximum or absolute minimum. The idea being an absolute maximum is to the farthest right, an absolute minimum to the farthest left. Okay, so the candidates test, as a result, we're looking for absolute maximum and minimum. We apply the candidates test to locate when an object is farthest from the origin. We determine the velocity v of t equals x prime of t. We set v of t equals 0 and solve for t. And we plug each candidate time into x equals t and evaluate. And then lastly, we compare the values of x equals t for each specific candidate. So really, everything we're doing in this specific lesson is all that we've been doing in Unit 3, just now from the perspective of physics. Lastly, we come to our last condition. Our last thing we're interested in seeing is speeding up versus slowing down. So this is where we need to be careful with acceleration. We tend to think of acceleration as strictly going faster, but acceleration can also correspond to slowing down, since acceleration is a change in velocity, and slowing down is a change in velocity. So this is a very abstract concept. So to help us think about this, we'll think about it from the perspective of a car. If a car speeds up, the gas pedal provides a pulse of acceleration in the same direction. This should say same, not opposite right here. So if a car is speeding up, the gas pedal provides a pulse of acceleration in the same direction of motion, aka the same direction as our velocity. If the car slows down, like we see right here, the brakes of the car provide a push in the opposite direction of the motion, which is what you feel when you're slowing down. So in this case, our acceleration will be pointing opposite the direction of our velocity. So we can use this to create conditions or generate conditions for speeding up versus slowing down. So if our object speed is increasing, we're speeding up, that means our velocity and acceleration must have the same sign, either negative negative if we're heading to the left or positive positive to the right, indicating that the pulse of acceleration is in the same direction as our motion. Now, if our speed is decreasing, we're slowing down, our acceleration is going to have the opposite sign of our velocity, indicating that our car is braking and providing a push of acceleration in the opposite direction of motion. And lastly, if we're moving at a constant speed, that means that our velocity is not changing at all. Thus, our acceleration will be equal to 0 at that point of interest. And these are the conditions you need for speeding up and slowing down.